Kia ora. What does a carbon-13 spectrum look like and what can we learn from it? Now you can see it's quite a bit different from the infrared. It has much narrower peaks than the squiggles. Also notice that the unit is parts per million, and that's just to make sure that every machine will give the same spectra for the same molecule. And we talk about chemical shifts, so we talk about upfield and downfield rather than higher and lower. The way the peaks work, we look at the nuclei of carbon atoms. So it's not the bond, it's the nucleus of the carbon atom. So be careful when you word your report that you are referring to the carbon atoms and not to the bond. The more shielded the carbon nucleus or the carbon atom, the more electrons it's got around that carbon nucleus, and so it is not affected as much by the signals, and so the more upfield the peak. If it's bonded to an electronegative element or a double bond or a triple bond, then it becomes less shielded and therefore it is more susceptible to the signal from the radio waves, and so it goes downfield. So these peaks are spread out. The height of the peak doesn't make any difference, although usually the tall peaks have got more hydrogens attached than the shorter peaks. So we divide the spectrum, the spectrum into four areas. The more upfield is carbon bonded to hydrogen or the less electronegative halogens and other carbons. Then between 50 and 100 is more or less where carbon is bonded to an oxygen so that the carbon atom is less shielded. Then it comes to the carbon-carbon alkene area where each carbon of that double bond is even less shielded, so it shifts down to between 100 and 150. And notice we can differentiate between whether it's a terminal alkene, so a carbon bonded to two hydrogens, or a carbon with hydrogen and another alkyl group, or both alkyl groups. They start shifting down. Then we have the carbonyl carbons, the amides, the esters, the carboxylic acids and acyl chlorides tend to be over here, and then the aldehydes and ketones tend to be above 200. So here's an aldehyde or ketone. Notice the peak above 200, and notice we've divided them up into the sections of 50 to 100, 150 to 200 and above. Always ask yourself how many carbon environments. There are 4 peaks here, which means there are 4 carbon environments, so you know there are at least 4 carbon atoms present in the molecule. These will be the alkyl ones, carbons attached to hydrogens. Normally the most upfield are methyl, and the ones more downfield are attached to other carbons, or this peak would be one attached to the carbonyl carbon. So this is the carbonyl carbon, and this is the carbon attached to the carbonyl carbon. Notice you must state what's absent, so the alkene is absent, and all these other carbonyl molecules, carboxylic acid, ester, amide, acyl chloride, are also absent because there are no peaks between round about 160 to 200. And this is the actual aldehyde, the molecule, and you'll notice that the first molecule is the most downfield one, is the carbonyl one, that's the aldehyde. Then the next one is the one that's been deshielded by that carbonyl, so it's the next one. And then the more substituted carbon is number 3, and then the methyl groups, the ones with the most hydrogens, are the most upfield. So here we can look through various examples. So the first one we're going to be doing is, if we're looking at, say, esters, acyl chlorides, carboxylic acids, or amides, they would have peaks down here. So the first thing you look at, what's absent. The ones very far down are not there. The next group is this, so you don't know which ones they could be, but you'd use your IR to support you. The alkenes are absent, they're in this group. Then you say, well, this could be a CO. Okay, yep, so that would be 60, so it would probably in this area. This one could be the carbon next to the carbonyl, and these would be then the alkyl groups, this top bit over there. And again, you would say there are 5 peaks, so there are 5 carbon environments, so at least 5 carbon atoms present. And this is the molecule. You can see that this is number 3, which is that peak over there. It's one next to the carbonyl carbon. The methyls are quite upfield, and that methyl is furthest away from the carbonyl and the oxygen, so it's the most upfield. So this is actually an ester. Okay, here's another example. So again, we say those are absent. We know these are carbonyl carbon. We'd look to the IR to see which type. We know alkenes are absent, and we can see there are a lot of peaks there. You don't have to identify every single one. But again, you have to ask yourself how many carbon atoms or how many carbon environments. And this, if you want to know, is what it would look like. This is an amide. And so, yep. So here's the next one, which is an alkene. It's a wide difference between them. So this would be your terminal alkene. This one, carbon of the double bond, would be more substituted. So again, you would click through and see which ones are present, which ones are absent. This one, because it's so downfield, is probably a carbon bonded to 2 alkyl groups, whereas that one is bonded to 2 hydrogens. We know we don't have an oxygen present because there's nothing here, and those would be your alkyl groups. Right, so that is the molecule. So you can see this carbon atom had 2 alkyl groups on it. The other carbon atom of the double bond has had 2 hydrogen atoms. The alcohol, this is the final one we'll look at. We'll notice there are no aldehydes or ketones, no carbonyl compounds, no alkenes. And now we see this peak between 60 and 80. That's the alcohol. Could be perhaps one of those. And then we have the alkyl groups. And you could try and match them, but it's not so important. But you should be able to see that the most upfield one is the methyl. So hopefully that gives you a bit of an overview of how to interpret your carbon 13 NMR spectra. Kia ora.